Hello everyone, welcome to PSE for Speed YouTube channel. In this video, we will show you the steps of sustainable process design through the demonstration of associated tools. The main tool is ProCAFD. It is linked to many other tools in the different steps of the sustainable process design workflow. For the demonstration, we will use the well-known head process as a case study. Now, let's get started. In this demonstration video, I will show you how to use ProCAFD to perform the sustainable process design. Now, let me first briefly introduce you ProCAFD. ProCAFD, where CAFD is from chemical process analysis, design, and synthesis. The aim of ProCAFD is to suggest a suitable process design. Let's say that we have a raw materials and we want to get the product. The green box in the middle is the process of reaction and separation. ProCAFD can tell us which process should be in the green box in middle. The software can screen the possible processing alternative route, and it also can rank the processing alternative route in terms of the energy, carbon footprint, and etc. After we have selected the processing route that match our interests, we can also use ProCAFD to connect to the commercial simulator, such as Pro2, for a more detailed simulation and calculation. So, this software will be very useful to design the process at the initial steps, where there is not much information in the green box. Moreover, the additional functions, such as the economic analysis, LCA analysis, safety analysis, and heat integration can also be done in here. ProCAFD software is designed to have 12 steps for the user, which make it very easy to use. The steps are divided into 3 stages, mainly includes synthesis stage from step 1 to step 5, which the alternative flowsheet is generated during this step. The second stage is design and analysis stage, where the design of the process unit and the analysis of econ, LCA, and the safety is performed during this stage. The last stage is innovation stage, where we generate and verify various sustainable alternatives generated by using the targets for improvement from the design and analysis stage. As mentioned earlier, we are going to use ProCAFD to generate sustainable designs for the HDA process. The HDA process, or toluene hydrodealkylation process, is the process that produces benzene from toluene and hydrogen. The reaction of this process is highly exothermic, which operate at high temperature around 600 to 850 K and pressure around 34 bar. Since HDA process has many process alternatives that can produce benzene, we can use ProCAFD in order to find the best process alternative, and all of this will be demonstrated in ProCAFD. Firstly, for this process, we need to know the chemical system, temperature, pressure, and reaction data, which is given in the table on the right-hand side here. Now, let's open ProCAFD. This is the ProCAFD, which supports the Windows operating system. So double-click here. Now, this is the starting interface of the ProCAFD, where we can select whether we want to create a new project or open the Save Project files. So, I will click Create New Project here to show you how to give the input data to ProCAFD. So, now we have entered the main interface of the ProCAFD. On the top, we can see the tab in here, which the users can easily follow the first step to the last step. Now I'm going to give the input data, which consisting of the compound data, the inlet and outlet stream data, and the reaction data. So, for the HDA process, there will be hydrogen, which I will give the CAS number. The second component is the methane. The third component is the toluene. The fourth component is the benzene. And the last component is the biphenyl. Next, we need to give the information for the stream data. So, in this process, there will be two inlet streams consisting of the hydrogen and methane gas and the toluene. And the four outlet streams consisting of the unreacted hydrogen and methane gas, the unreacted toluene, the benzene product and the biphenyl byproduct. We can click on the arrow here, to give the information, which consisting of the temperature, the pressure and the composition. So, the first inlet is the hydrogen and methane at the 34 atm. The hydrogen composition will be 0.9. The methane will be 0.1, with the rest of them as 0. Then after we have finished we save. Next is the toluene stream at 34 bars. So, toluene composition will be 1. After we have given the information for the inlet streams, the reaction data here will turn red, which indicates that the reaction data need to be provided. So, next we will give the information for the outlet streams. The hydrogen would be 0.5 and the methane will be 0.5 as the assumed values for the first stream. Then for the second outlet stream will be toluene. Then for the third outlet stream, it will be the benzene product. And the last outlet stream will be the biphenyl product. Next, we need to give the reaction data. So, we click here. In this tab, the software will allow the user to add the reaction data by giving the stoichiometric numbers, or the order of the reaction in terms of the kinetic reaction or the conversion reaction, depending on the user's need. In this HDA project, there are two reactions. The main reaction is that hydrogen and toluene will react. So, we give the hydrogen and the toluene. So, the information for the reactant will show in here. Then the hydrogen will react with the toluene to give the benzene, and the methane. So, the information for the product will show in here. The next we have to give the conversion data, the temperature, and the pressure in here. So, the reaction temperature is 639 with the pressure of 3400. The conversion for the toluene in this reaction is 0.75. Then we save reaction data. Next, we will give the second reaction data. So for the second reaction data, moles of benzene will react with to become biphenyl and the hydrogen. The temperature and the pressure data is the same and the conversion of the benzene to the biphenyl and hydrogen is 0.15. Then, we click Save the reaction. After we have provided two reactions data, we close this window. Then, we can see that the reaction data tab, here, it will turn green, which means that we have given all input data. Then, we can proceed to the next step by clicking Next here. After we click Next here, the program is trying to take all the input data that we have given, before to generate all the useful information for the sustainable process design. This step will take some time, and when the calculation is finished, we will enter to step 2, which is the mixture analysis. Now, the calculation has finished, and we are in step 2, the mixture analysis. All of the analyses are divided into 4 blocks, here. The first block is the mixture analysis report, where the mixture analysis report can estimate the mixture condition at a given temperature and pressure. Next is the analysis block, which we can look at 3 options: the azeotrope analysis, the driving force diagram, and the eutectic point analysis. For the azeotrope analysis, the software will take 5 compounds that we have given earlier. Since there are 5 compounds in the system, there are 10 binary pairs of the compounds can be generated. So, we can look at whether each binary pair is formed azeotrope or not. Next is the driving force diagram, where we can look at the plots, here, to see how easy the separation for each binary pair is. Next is the eutectic analysis, which we can look at the eutectic analysis data for each binary pair here, whether the eutectic is available or not. Next block is the binary ratio matrix block, where the properties of the pure compounds are taken from the database. Then, this table will show the binary ratio of the property for each binary pair. For example, the melting point, the boiling point, or the solubility parameter, and many more. After that, all of the mentioned 3 blocks analysis here will be used to generate the feasible separation technique for each and every binary pairs, as we can see in this table, here in this block, which feasible separation technique can be used for this process for this system. Then, we go to the next step. Now, we are in the step 3a, the process group selection. All of the information from the mixture analysis have been translated to generate the process group selection. According to the process group concept, there are 4 types of process groups: the inlet process group, the outlet process group, the reactor process group, and separation process group. For the inlet process group, we have defined the hydrogen and the methane as one feed, and the other feed is the toluene. For the outlet process group, we have defined 5 compounds for the outlet stream earlier. From the reaction analysis, there is the reactor process group, which has an outlet of the 5 compounds. For the separation process group, the software had taken all of the feasible techniques. From that, all of the process group initialized with different compounds are listed in this table, here. We can also look at the number of the inlet, outlet, separation, reaction, and the total process groups, in here, which is the number of the total process group is 175. Then, for the next step, which is the process group selection in the step 3b here. In this step, we can use the process group option to select only some process groups. For example, we select only the non-membrane solution, or we select only our separation tasks as distillation, or we select only the individual separation tasks. But first, let me go to the next step to show you all the generated feasible flow sheets. In this step, the software will show all of the possible flow sheets with different alternative process groups. As we can see that this alternative flowsheet group is similar to the SMILES representation of the chemical compound structure. So, each and every string in here represent a different flowsheet for the HDA production. Then, we can see that there are 340 generated flowsheets here, with different separation task process configuration. The user can also click View here, to see the process flowsheet in ICAS, a process simulator. Here is how the flowsheet will look like, which consisting of the reactors and 3 separation tasks. Now, let me go back to the process group option. So, now I will choose our separation task as distillation and flash only. Then, we click Next. Now, we can see that the number of the generated process flowsheets will be reduced to 10. Which there is only flash and distillation column as the separation task in here. We can click Superrow here. Then, the ProCAFD will convert the feasible flowsheet to Superrow, which Superrow is one of our in-house software tools that is used for the optimization of the superstructure. Here is the superstructure for the HDA process with only distillation and flash as the separation tasks. Now, let me close this and we go to the next step, which is the ranking step 5. In step 5 here, all of the feasible flowsheets are ranked in terms of the performance criteria, which consisting of the energy index, carbon footprint, the product recovery. We can rank the flowsheet by clicking at the top of the column. For example, if we are going to run the energy index from the lowest to highest, then we can right-click here, and then select the flowsheet of interest. Then, after we select the flowsheet, we can go to next step, the design and the analysis. Next, step 6, design and analysis. In this step, the mass and energy balance need to be performed. To do that, we can click Calculate here for mass balance. And click Calculate here for the energy balance. We can look at the decision variables and operation design in here. For the decision variable, the data is calculated based on the saturated vapor and liquid data. The calculated temperature and pressure will be obtained through the dew point and the bubble point of the compounds. For the operational design, the information and the column specification are given in here, calculated using reverse design method. We can also look at mass balance and the engine balance information in the table in here. Then we go the next step, the rigorous simulation. In this step, the ProCAFD is connected with the commercial simulator, which is the Pro 2. We can export this alternative flowsheet by clicking Generate here. Now, the Pro 2 will show up, and here is the generated flowsheet from the ProCAFD, which is converted to Pro 2. We can try to run the simulation in here. But unfortunately, this simulation may not be converged in the first run because some of the default convergence criteria need to be adjusted. So, let me close this flowsheet and open you with the adjusted convergence criteria flowsheet. After we have adjusted some of the current default convergence criteria, we can see that the convergence will be reached faster. Then, after we have finished doing the calculation in the simulation in here, we will export the simulation data back to the ProCAFD. In order to do that, we can go to the output in here, and then we click Generate Excel Output. Then we click Yes. So, the Pro tool will generate the Excel output report, which we will import this Excel output in the ProCAFD for the further step. Here is the Pro 2 summary report. Then, we go back to the ProCAFD. Then we go to the next step, the process analysis. Now, we can click Import here, to import the summary report from the Pro 2. Then we go to the directory of that simulation. Then, here is the summary report of the Pro 2 from the simulation sheet that we have imported previously. So now the software will read all of the stream data and equipment data from Pro 2, such as the flow rate, temperature, pressure, which all of this information will be used for the further analysis. Now we click Next to go to the next analysis. Then, the first analysis is the economic analysis. All of the stream and equipment data that we have imported previously need to be exported to the Econ. Econ is the one of our software tool that is used for the economic analysis. In this step, the user needs to create the Econ input file and provide the necessary data. For example, such as the cost data, the raw material data, the product cost data, the sizing parameter, and many more. In this case, I have already prepared the Econ input file for the HDA process. If you click Import Econ input file, select my Econ input file here, then I will click Generate Econ output file. The Econ output file is the macro Excel Econ tool, which is one of our software tool that is used for the economic analysis. Here is the interface of the Econ, which the user can use the Econ to perform the cost calculation for the capital cost, the operating cost, and the economic analysis. First, the input file will be located at this directory. So, we will click Load the file, here. Then, the Econ tool will use the data from the Econ input file to generate the raw material, the product, and the equipment data for the Econ tool. So, now we need to give the information for the heat exchanger, as one of the equipment. So, we will select this heat exchanger type as the double pipe heat exchanger. If we click OK, then the material will be the carbon steel tube and shell with the pressure up to 30,000 kPa. The heat exchanger area is 100. So, the Econ will automatically calculate the purchase cost for this equipment. Then, we click OK. Next, we need to provide the utility information data, which this heat exchanger will use the core utility, with the process cooling water as the core utility. And then the heat duty is 140 for example. Then we click OK. Now, we can see that the information that we have provided to the Econ will be shown in here, which the equipment will calculate the capital cost and the utility will also be calculated as the utility cost. Then, for the further strp, the user have to insert the information of every single equipment by using the Econ tools. Since I have already prepared the finished Econ output files. Now, let me go back to the ProCAFD. Then, I will click Import Econ output file and locate it to the finished file I have prepared. Then, I will look at the raw material and the product data from the file by clicking here. So, the ProCAFD will show the information of the raw material and the product of this process, which consisting of the quantity, the price, the annual price, the total raw material, and the product annual price. Next, we can look at the equipment and the utility data of this process. So, we can look at the purchase cost of the equipment data. We can also click here, to show the plot, which the pie diagram here can show the contribution of each equipment which is making to the process. In the same way for the utility cost, which we can look at the information in this table here. We can look at the plot, the pie chart plot here, and look at the contribution that each utility cost has made to the process. Next is the capital costs and operating costs. So, we can also look at the capital cost and the operating cost in here. We can click the plot here to see the pie chart of the capital cost and the operating cost, which in the same way will show the contribution that each parameter is making to the process. Then lastly, we can look at the economic evaluation. The economic evaluation will show the cumulative cash flow for this process, which from the curve it can be observed that the break-even point can be reached for this design at approximately 4.5 years. Then we will go to the next step. Then, the next analysis is the sustainability analysis. The ProCAFD can calculate the sustainability indicators using the Sustain Pro. The first step is that we need to select the main product, which is the benzene, and the waste product or the byproduct produced is bifuel. So, the ProCAFD will use the information from the summary report that we have imported previously and automatically fill in some of the results, such as the production rate, total feed rate, total waste generated, total energy from heating, and electricity. Then, for the total water required, which is 550,000 kg per hour. The number is approximately taken from the rigorous simulator flowsheet. Now, we click Calculate it. Then, the program will do the calculation for the sustainability indicator as shown in this table here. Then, we go to the next step. This step is the analysis of the life cycle, which the environmental indicator is shown here in this table. The ProCAFD can calculate the environmental indicators such as a human toxicity, also deployation, global warming potential, and many more based on the flow of the inlets and outlets of chemicals. So, if we look carefully, the last row here, this is the impact generated. The green box here indicates that the inlet of this indicator is higher than the product, and the red box here indicates on the opposite side, where the inlet of the indicator is lower than the product. Then, we go to the next step. This step is the footprint analysis step, consisting of the ecological footprint, the water footprint, and the carbon footprint. Let's start with the ecological footprint, where we can select the country of interest. For example, Thailand, and then, we select the unit GHA per person. Then, we click Calculate. Now, ProCAFD will calculate the ecological footprint for Thailand in this unit. We can try to select more, for example, Denmark with different unit. Then, we can click Calculate. So, Now the result for Denmark with the GHA unit will be presented here in this table. Next is the waste footprint, in the same way that we can select the country that we are interested, for example, France, with agriculture. So, the total water required is here. Then, we click Calculate. Then, the water footprint will be shown here in this table for France with the agriculture type. The next footprint is the carbon footprint. The ProCAFD relates all of the unit equipment that required heating and electricity in this table here. We can also select the utility source in here. So, let's say that we will use the default unit. Then we click Calculate it. So, now the ProCAFD will do the calculation for the carbon footprint of each equipment that require heating and electricity. Then we go to the next step, which is the safety analysis. In this step, the ProCAFD can calculate the Chemical Inherent Safety Index, or the LCI, and the Process Inherent Safety Index, or the LPI. If we look at the table below, the ProCAFD will use the property data from the data bank, such as the flash point, boiling point, the UEL, LEL toxicity limits, for the calculation of the safety index. For this process, we will select the reaction 1 as the main reaction. Then, select the reaction 2 as the side reaction. The construction material will be the carbon steel. Then, we will select the chemical interaction as the explosion. We select the process structure as no data or neutral. Then, for equipment safety will be a cooler, reactor. And for equipment safety, it will be atmospheric storage tanks and pumps. Then, after that, we click Calculate. Now, the results of the LCI and LPI will be shown in this table here. Then, we go to the next step. This step is step 9. The overall result. In this step, we can look at a plot of the overall result by clicking Plot or Result here. We can look at the plot of the utility cost for each equipment, the energy consumption and the carbon footprint for each equipment. We can see from the plot that which equipment have utility costs and consume high energy, which it can be observed that the compressor and the heat exchanger between the reactors consume the high energy. To overcome this hotspot, we can use the concept of the simultaneous heat integration and process optimization, which I will show you next. After we have gone through the synthesis stage and the design and analysis stage with 9 steps through ProCAFD, now we are going to perform the simultaneous heat integration and process optimization for the innovation stage in the next part. Also, we will generate reactive distillation options and verify them through simulation. After we have gone through the synthesis stage and the design and analysis stage with 9 steps through ProCAFD, now we are going to perform the simultaneous heat integration and process optimization for the innovation stage in the next part. Also, we will generate reactive distillation options and verify them through simulation. Firstly, we need to set the objective function for the optimization. The objective function is the profit, which is equal to the revenue minus cost. The revenue are from the sale of products and byproducts, and the costs are from the raw material price, utility cost, and the purge penalty. This table shows the numbers that are using for the profit calculation. This slide shows the HDA simulation flowsheets from ProCAFD with improvement through the sequential heat integration and optimization. From the flowsheet, the purged gas split fraction is optimized and some of the hot and cold stream can be recovered through the heat integration. With the sequential approach, the profit can be obtained at $1,004.32 per hour. However, since the heat integration and the optimization is not performed in the same time simultaneously, we may not get the optimal solution because the heat integration are not considered during the process optimization. But, if heat integration and process optimization simultaneously, the fully optimized results could be found. Now, I will show you the use of PSE for speed heat integration module for the simultaneous approach with a Viva Pro 2 simulator in the next slide. This slide here shows the simultaneous heat integration and process optimization by using the PSE for speed heat integration module as the user-added module in Pro 2, as highlighted in the red box here. The module will find the optimum heat integration and transfer the results to the optimizer in Pro 2 to find the optimal operation condition in the same time through the heat integration module to perform the simultaneous approach. The profit can be increased by $1,147.13 per hour. The heat integration module will generate the output results in terms of hot and cold heat duty, where the utilities are still required for heating or cooling. Then, we will use the output results from the heat integration module to validate in Pro 2. By rearranging the flowsheet corresponding to the heat integration module output results with the optimized purged gas split fraction, the profit that we can get is $1,147.19 per hour, which confirms the results of the heat integration module. These results imply that the simultaneous heat integration and optimization with the PSE for speed heat integration module tool can improve the process, thus increasing the profit of this HDA process. More details and information of the simultaneous heat integration and process optimization can be found at the simultaneous heat integration and optimization video in PSE for Speed YouTube channel. Next part in the innovation stage is the process intensification and hybrid scheme, which is step 11 to step 12. In this part 1 will explain the concepts, the workflow method, as well as the set of rules of the reactive distillation and the hybrid scheme, and briefly show one case study for the process intensification through the reactive distillation column example. Reactive distillation is a chemical process that combines the unit operations of reaction and distillation into a single step, in order to simultaneously convert the reactants into products and separate the reaction products from the reactants. In reactive distillation, a chemical reaction takes place in a distillation column, where the reactants are continuously fed into the column, and the products are continuously removed. To apply the reactive distillation column or RDC, we have to apply the workflow shown on the left-hand side. First, we apply the set of rules and based on the answer, decided if RDC is feasible or not. Then, if all the answers are yes, then we go to step 2, process intensification, to design the RDC that will match the process specification. Then, we go to step 3 to apply the target-based process improvement methods to obtain the final sustainable process design. So, there are 7 rules that needs to be satisfied to apply the RDC, as shown on the table on right-hand side, here. The first rule is the reaction exothermic? Yes, it needs to be exothermic so it will generate vapor. Second rule, is there only one reaction? Yes, note that also multiple simultaneous reactions can be considered, as they will require one reactor. The third rule: does the reaction and separation involve liquid and vapor phases? Yes, so we have liquid and vapor phase in the reactive separation. The fourth rule: does the separation involve the azeotropes or close boiling pairs? Yes, then there is incentive for the use of RDC. The fifth rule: does the separation involve 3 or more products? Yes, so there will be 2 or more product streams. The sixth rule: is a high purity product desired? Yes, that is the incentive to use the RDC. The seventh rule: are there energy-intensive separation or waste issues? Yes, that is also the incentive to use the RDC. If the process is matched with these 7 rules, then the RDC can be replaced the original process, and the use of RDC means use of process intensification. So now, I will show you the case study of the process intensification by applying the reactive distillation column for the methyl acetate production. Here is the flow sheet of methyl acetate production, as shown on the left-hand side. The reference process consists of the reaction part and separation part. For the reaction part, the acetic acid is reacted with methanol to produce the methyl acetate and water. After the reaction, the products and unreacted reactants are going to the separation part to separate the reactants and the products. Since the target purity of the products for this process is very high, a large amount of the energy is required for the separation part. Also, the process requires too many separation steps. Thus, the aim of this problem is to reduce the number of the unit operations as well as reduce the energy demands and improve the environmental impacts. By checking the set of rules for this problem, this process is matched with all the rules, so that we can convert the whole process to RDC. For the base case design, which is the flowsheet on the left-hand side, the process hotspot for this process can be identified, as shown in the picture, where the large amount of the energy are consumed in the wrap boiler of the distillation column in the separation parts. After applying the RDC, the reactors and several distillation column can be converted to a single reactive distillation column, as shown on the right-hand side, which the reactive distillation column can perform both the reaction task and separation task in the same column. Thus, many of the wrap boiler unit in the base case can be converted into one single wrap boiler for the RDC, which the wrap boiler duty can be reduced from the base case at 18,333 kilowatts to 1,803 kilowatts, which is approximately 90% in reduction. Moreover, the capital costs were reduced by 45% and the operating costs can be reduced by 20% since the utility cost is reduced by 91% after performing the process intensification with RDC. We also has developed some of the other case study using the reactive distillation for the process intensification, as shown in the table in this slide here. For the case study of the methyl chloride production, after applying the RDC, as shown in the configuration 1 case, the energy consumption can be reduced from 146 to approximately 18.13 MW, and the methyl chloride product purity is also increased, compared to the base case. By replacing the distillation column with membrane, as shown in configuration 2 case, the energy consumption can be reduced to 14.41 MW. For the case study of dioxylane production, by applying the RDC, as shown in alternative 1 case, the energy consumption can be reduced from 1.03 to 0.873 MW. Then, by replacing 2 distillation column with the divided wall column, which is one of the process intensification, the energy consumption is reduced to 0.726 MW, as shown in the alternative 2 case. For alternative 3 case, by applying the reactive divided wall column, the energy consumption can be drastically reduced to 0.359 MW, and the higher purity of the produced can also be achieved. Lastly, please note that all of the simulation files in Aspen Plus for verification of these case studies that were presented will be supplied as part of the software package. Next is the hybrid distillation scheme or SDS. As we know that distillation is one of the most used separation techniques in the chemical process industry. However, it is also the separation technique that uses most energy, as we can see from the first figure. The distillation is a very efficient technique for the separation, but only until a certain purity. The second figure on the left-hand side below here show the plot of the product purity versus the Rapp-Euler duty in the distillation column. We can see that the Rapp-Euler duty until the point A is very good. However, it consumes a very large amount of energy required for the separation in going from point A to point B. So, if we use the distillation until the point A, and we replace with something else that require less energy from point A to point B. For example, the membrane. This is the idea of the hybrid distillation. The third picture here in the center show the configuration of the hybrid distillation. The distillation is used until the product purity reached at point A, and then the membrane is used to separate the high boiling compound as the permeate to further increase the product purity to point B as the retentate. So, there are 7 rules that need to be satisfied to apply the hybrid distillation scheme, as shown on the table on the right-hand side, here. The first rule is a high product purity obtained as a distillate. Yes. The second rule, does the host column have 1 feed and 2 products? Yes. The third rule, is the separation difficult? Yes, the more difficult, the more incentive to use the hybrid operation. The fourth rule, based on the cutoff equation, is the potential serving more than 20%? Yes, it can be easily noted in the figure on the left-hand side. The fifth rule, is the feasibility of the other separation technique in the SDS confirmed? Yes. The sixth rule, the mixture to be separated does not involve the azeotropes? Yes. The seventh rule, is a retrofit alternative desired? Yes, that is also the incentive to use the SDS. If the reference process is matched with these 7 rules, then the SDS can be applied to the distillation column. By the way, in this presentation, the case study HTA process using in the hybrid distillation scheme has not been considered. With this slide, we highlight the hybrid scheme for further reduction of the energy demands. The method first identifies the most energy-intensive separation process, and then applying the rule. If the match of the design target is found, then the significant energy savings are possible through the hybrid scheme. Our application with the hydrocarbon processing by distillation show that between 20 to 40% energy can be saved. Now, I will end the presentation and the demonstration of ProCAFD with the case study for the sustainable process design. We hope you found this presentation interesting, and please subscribe to our YouTube channel to remain updated on the new additions to PSE for Speed YouTube channel. Thank you for your time and interest in our video.